Hi, welcome to this video. In this video, I'm going to discuss about the units and dimensions, followed by the concept of mole and molecular weight. Then, given a composition of solid mixtures or ideal gas mixtures or liquid mixtures, representing the concentration in terms of mass or mole fraction and calculating average molecular weight and density. Dimension represents quantities like length, mass, and time. The units are measures of dimensions like meter for length. The units can be classified into fundamental units and derived units. The fundamental units are length, mass, time, and temperature. The derived units are obtained by the combination of the fundamental units. Examples: volume, gravity, and speed. When we have a large or very small quantity of substance, we'll be adding a prefix for easy representation of those values. For example, when we take very small quantity of a substance, we can mention using micrograms, or if a little higher, then we can use milligram or gram or kilogram. Similarly, for all other dimensions also, we can add this prefix for easy mentioning. Different system of units were used for easy processing and measuring the dimensions. They are CGS system, FPS system, MKS, and International System of Units, which we are following now. So in case of FPS, the length will be mentioned using feet, and the weight will be, that the mass will be mentioned using lb. These are the primary units in SI systems. Specific to biochemical engineers, we will be using more on amount of substance, that is mole, time, mass, and length we will be using in our system. So these unit conversions can be useful for later solving problem. I suggest you to take a photograph of this and keep it with you. Moving forward, we are going to discuss about the mole and Avogadro's number. For better handling and easy measurement of any substance, we define a term called mole, which defines as the amount of substance that contains 6.022 into 10 power 23 of entities. These entities can be atoms or molecules or ions, etc. This 6.022 into 10 power 23 is called as Avogadro's number. Followed by defining the mole, the mass of 1 mole of substance is termed as molecular weight. The unit can be gram per gram mole. Using this relation, given a substance mass, we can find how much moles are there inside the mass of substance. So let's take an example to understand this concept. The question says, calculate the number of moles in 100 grams of water. So now what is the given data here? The given data is in mass, and we're going to use the molecular weight as I already told you. In this case, for water, it is 18 gram per gram mole. So now let's use this particular relation and rearrange that so that we can calculate the number of moles. Number of moles can be calculated by the ratio of mass by molecular weight. In this case, mass is 100 gram, molecular weight is 18 gram per gram mole. So we'll be getting 5.56 gram moles of water in 100 grams of water. Moving on to next concept is molecular weight and average molecular weight. When we are working with a mixture, we cannot say one single molecular weight because it has multiple components in it. When it has multiple components, then we have to go for average molecular weight, which can be calculated by this formula: the total mass of the whole substance divided by total number of moles present in the particular mixture. So this can be used for in the upcoming problems also. The tabulated elements and compound will be used for future problem solving, so you can take a screenshot of this particular value. In examination point of view, these values will be given in the question paper itself. The next topic to discuss is mass fraction. The mass fraction of A is like percentage of marks out of 500, how much we are getting. Similar to that, mass fraction of A can be calculated. The mass fraction of A will be given by the ratio of mass of A in the mixture divided by the total mass of the mixture. And when we multiply the mass fraction by 100, we get mass percentage. Similarly for mole, so number of moles of A in the mixture and divided by total number of moles in the mixture. As we calculated mass fraction, mole fraction, we can calculate volume fraction or volume percentage also, which will be given by volume of A divided by total volume of mixture. Next, we're going to discuss about ideal gas volume and density of mixture. The volumetric behavior of a gas system at low pressures like 1 atmosphere can be calculated using this equation called as ideal gas equation, where pressure into volume will be equated to number of moles of particular component into gas constant into temperature. To find the density of a mixture, we have to introduce a density term into this particular equation. We know that the mass by volume is equal to density. So this volume will be replaced by mass by density in this particular equation. By this way, I bring density into this equation. When I rearrange this density and N, I can get mass by n as molecular weight. On rearranging, I can find the density of the mixture. This molecular weight is average molecular weight. As we already discussed, when we have a mixture, we have to use average molecular weight. When we are working with ideal gas system, the mole percentage will be equal to pressure percentage and volume percentage. The choice of R value depends on data what we are handling in a problem. We have seen enough definitions to solve problem. So I'm going to solve 3 problems in this particular lecture. The first problem will be on solid mixture. So we are expected to find average molecular weight. So let's read the question. A dry solid mixture contains 30 gram of sodium chloride and 40 gram of NaNO3 and 30 gram of KCl. Now we are asked to calculate the average molecular weight of the solid mixture. So there are many ways to solve this problem. So what I'm going to suggest is forming a table and solving. This makes solving the problem easier, and also it helps in avoiding errors. Now you form a table and list out all the components that are given in the system. So in this case, NaCl, NaNO3 and then KCl is listed, and the respective mass is entered in the next column. Now whenever you are dealing with mass, moles, volume, you just sum it and put at the bottommost row. In this case, mass is given, so I have written all the values and summed at the bottommost row. Once I know the mass, I can find the mass fraction. So mass fraction can be calculated by mass by total mass. The total mass you just calculate by summing up all the masses. So the individual mass is 30 in case of NaCl, and we are dividing it by 100, that is total mass. We'll get 0.3. Similarly, I do for other 2 components, I'll get this particular value. Now I want to convert this value into mole fraction, right? So I'm just using molecular weight because molecular weight relates mass and moles. So I'm writing the molecular weight in the center of the column. Usually it will be given in the question. By rearranging this equation, I can get the number of moles. So number of moles is equal to the ratio of mass of substance and molecular weight. In this case, the mass is 30 for NaCl and the molecular weight is 58.44. So I'm finding the ratio, which comes to be 0.51. Similarly, I find for other 2 components and I'm getting this value. Since it is number of mole, as I told you, either it is mass or volume or number of moles, we have to sum up and put it in the bottommost row. So it's summing up, I'm getting 1.38. So now to find mole fraction, the number of moles divided by total number of moles will give me the mole fraction. So the number of moles is 0.51 for NaCl. The total number of moles is 1.38, so I'll get 0.37. Similarly, I do for other 2 components. Now I have calculated the mass fraction and mole fraction. Let's move on to average molecular weight. To recall the average molecular weight formula, it is the ratio of total mass by total number of moles. In this case, the total mass is 100 and total number of moles is 1.38. So the ratio will give me the average molecular weight, which is equal to 72.46 gram per gram mole in this particular problem. So we solve the problem. We'll move on to the next problem where we calculate the average molecular weight and density of a gas mixture that behaves ideally. So let's read the question. A gas mixture at 1 atmosphere and 25 degrees Celsius contain the following gases in volume. So the data is given in terms of volume. So 2 liter of oxygen, 5 liter of nitrogen and 3 liter of carbon dioxide. So we are asked to calculate the average molecular weight and density of the gas mixture at given conditions. We have to remember that when we are working with ideal gas, then the mole percentage will be equal to pressure percentage and volume percentage. In this case, the data is given in terms of volume. So we calculate volume percentage and we can assume the volume percentage is equal to the mole percentage. Let's see how to solve the problem. As usual, we'll form a table and we list all the components, in this case oxygen, nitrogen and CO2. Now the next column, the given data. So the given data is in terms of volume. So I'm filling the volume 253 and summing it up 10. As I told you, mass, moles and volume, we will sum it up. To find the volume percentage, individual volume by total volume will give me the value. So 2 by 10 into 100 will be the volume percentage of oxygen. I will do the same for remaining other 2 components. I will get this value. As we are working with ideal gas system, so we can assume that the volume percentage is equal to mole percentage. So I'm just taking the same value here. Now on assuming the base is 100 moles, 20% of oxygen means 20 moles of oxygen. 50% of nitrogen means 50 moles of nitrogen. So this is called as basis. To solve the problem easier, we assume some basis. So in this case, I'm using 100 moles. So directly the percentage will be the equal to number of moles. As I told you, number of moles, I have to sum it up. So I just summed it and put at the bottommost row, which comes to be 100. Now you see the left hand side is full of moles. So right hand side should be in terms of mass. So to convert to mass, I need molecular weight. So I just listed all the molecular weight of these individual components. So I have listed here. Moving on, we rearrange the formula to calculate the mass. So mass can be obtained by multiplying the molecular weight and number of moles. The number of moles is 20 in case of oxygen and the molecular weight is 32. So I can directly multiply that. So once I calculate, I can put mass fraction and I can fill that column. So now we find the mass. So mass is equal to 32. I got 640. Similarly, I do for other two components and I sum it up. As I told you, volume, moles and mass, we will add it together. So we fill the bottommost column with the corresponding sum. Now mass fraction will be equal to the individual mass divided by total mass. So 640 divided by 3361.3, which is equal to 0.19. Similarly, I'm going to do for other two components and I filled it. Now we'll move on to find the average molecular weight. To find the average molecular weight, the formula will be total mass by total number of moles. In this case, the total mass is 3361.3. The total number of moles is 100. So the ratio will be coming to 33.613, which is the average molecular weight. Now we move on to density of mixture, which is given by pressure into molecular weight divided by R into T. In this case, the pressure is 1 atmosphere and the average molecular weight we just calculated, 33.613. And the denominator will be the R. So R value, I'm going to take 0.8206 because I'm using liter in atmosphere in this case. So I'm going to use 8.08206 liter atmosphere per mole Kelvin multiplied by, I have to have the temperature in Kelvin, but the question is given in degrees Celsius. So I'm converting into Kelvin by adding 273 with that. On solving, I'll get the density to be 1.37 gram per liter. Okay, we saw the next problem. In this case, again, we have to calculate average molecular weight and density. It is ideal gas system, but the data is given in terms of pressure. As we solved the previous problem, we form a table and we list all the given components and the respective given data. So in this case, the given data is pressure. So we know that in ideal gas system, the pressure percentage is equal to the mole percentage. So once I calculated the total sum of pressure, I can calculate the respective pressure percentage, which will be equal to individual pressure divided by the total pressure. So 2 by 6, which gives me 33.33. Similarly, I do for other two components, I find the pressure percentage. We are working with ideal gas system. The pressure percentage will be equal to mole percentage. So I'm directly taking the pressure percentage as mole percentage here. And assuming 100 moles as basis, I can directly use this percentage of mole as number of moles. So the number of moles of oxygen is 33.33. Accordingly, other two components also. As it's number of moles, I am finding the sum and putting in the bottommost row. Now the left hand side is completely the number of moles, so the other side should be mass. So to convert moles to mass, I am using molecular weight here. I listed down the molecular weight. As I already told you, the molecular weight will be given in the question paper hopefully. So when I know the number of moles and molecular weight, I can calculate the mass by multiplying the molecular weight and number of moles. In this case, I'm multiplying 33.33 and 32. I'm getting 1066.56. Similarly, I'll do for other two components. And as it is the mass, so I'm summing all the mass and I'm putting as total mass at the bottommost row. Now to find the mass fraction, I can use individual mass divided by the total mass. In this case of oxygen, it will be 1066.56 divided by 3201.21, which will give me 0.33. So I can calculate other two component values also. Now to find the average molecular weight, the formula is total mass divided by the total number of moles. Here the total mass is 3201.21. So the formula will be, so the average molecular weight can be calculated by finding the ratio of 3201.21 and 100. So it comes to be 32.01 gram per gram mole. Now we moving on to find the density. The formula for density is pressure into molecular weight divided by R into T. Here the pressure is 6 atmosphere and the molecular weight we just calculated 32.01 gram per gram mole. And the R value I'm taking 0.8206 liter atmosphere mole Kelvin. You may think that there are many R values are there. Why we are choosing this? In this problem, we are working with liter and atmosphere. So I'm just choosing an R value which has liter and atmosphere. And the temperature is given in Kelvin only. So I need not sum anything. So directly I'm substituting temperature here. On calculating, my value comes to be 7.86 gram per liter. So we solve the problem. Next lecture, we'll see concentration of liquids, that is molarity, molality, normality, and the problems on unit conversions. Thank you.